Now today, we have a very, very special guest with us who's come a long way to see us, but Will Happer is also in town to take part in a symposium over at UNC Chapel Hill, and as Will warned me when we were talking about this that he might be disinvited before he got here, but that's not the case. So he will be over at UNC today, but Dr. Happer is an exceptional scholar. He's professor in the Department of Physics at Princeton University and is a specialist in modern optics, optical and radio frequency spectroscopy of atoms and molecules, radiation propagation in the atmosphere, and spin polarized atoms and nuclei. And by the way, he graduated from the UNC, he has his PhD from UNC as well. So Dr. Happer, well, go into this, received his BS degree in physics from the University of North Carolina, and has his PhD degree from Princeton. I should have known better. He began his academic career in 1964 at Columbia University as a member of the research and teaching staff at the physics department. And while serving as a professor of physics, he also served as co-director of the Columbia Radiation Laboratory from 1971 through 1976, and director from 76 to 79. In 1980, he joined the faculty at Princeton University, and in August 1991 he was appointed Director of Energy Research in the Department of Energy by President George Bush. While serving in that capacity under Secretary of Energy James Watkins, he oversaw a basic research budget of some $3 billion, which included much of the federal funding for high energy and nuclear physics, materials science, magnetic confinement fusion, environmental science, the Human Genome Project, and other areas. And he remained at the department until 1993 to help the Clinton administration during the transition period. He was reappointed professor of physics at Princeton University in June of '93 and named the Eugene Higgins Professor of Physics and chair of the University Research Board from 1995 to 2005. And in 2003, he was named to the Cyrus Fogg Brackett Chair of Physics. So you can see our guest is an extremely distinguished scholar. Now, Dr. Happer's also done a bit of research on global warming, among other things, and today he's here to talk with us about the myth of carbon pollution. Dr. Happer.
Well, thanks very much, Corey, and my brother Ian and my wife Barbara are here with me today. They, I think, got a free meal out of this, I hope. And I have to say that, you know, the location is of special meaning to me and my brother because Ian's middle name is Morgan, so we're on Morgan Street. And because our mother's family, Morgan family, has been in North Carolina since before the Revolution, and we're very proud of that. So I'm going to talk to you today about the myth of carbon pollution. You know, I keep hearing people, even President Obama, and talking about carbon pollution. Let me just say right outset, they don't know what they're talking about. It's not pollution at all. And so anyway, carbon dioxide, that's what we're talking about normally, has been demonized because it supposedly causes catastrophic global warming. But I'll show you in a minute that the observations show that all the computer models that had predicted huge warming from CO2, they could hardly be more wrong. It's just unbelievable how wrong they are. And it's also pretty clear that what little warming there will be beneficial. And more importantly, there'll be huge increases in agricultural productivity. Things are going to grow better. They'll need less water. And so why you should call something that does this a pollutant just beats me. It's not a pollutant. Well, okay, I'm only a physicist, but Al Gore actually is a Nobel Prize winner for his time in science, and this is the cover of his most recent book, Our Choice to Save the Planet. You know, the current climate crisis, nobody can figure out what the crisis is, but he seems to think there is one. And this is a picture that Al says comes from a NASA photo. Well, I actually, some of the NASA astronauts are my personal friends, and so they helped me to find the original, and here's the original. This is a NASA photo. And you can tell it's the same photo Al used, but there's some obvious differences. For example, this real photo, the Earth is covered with clouds. There are clouds everywhere you look, practically. If you step back, here's Al's photo. So he's erased the clouds as much as he can. You wouldn't want people getting the idea that maybe clouds have something to do with the temperature of the Earth. You know, it's all that demon CO2. So, okay, so that's perhaps a minor thing. You can tell it's the same picture by simply comparing the cloud patterns. Are identical. It's exactly the same picture. But especially around the tropics, there are no clouds. And in fact, this equatorial region is always covered with clouds. You know, here it is down here. You know, there. Now, this is the outer cover of the book, and you can see there's a fold. It folds, and there's the binding of the book here. So you can open this cover, turn it over, and you can see the inner cover where he shows you what will happen if we don't listen to him. So here's what will happen. So here's the inner cover. He says, when you unfold the cover, the image you see in the Earth, as we know it today, with its deep blue oceans, rich soil, green forests, that's the cover. This side reveals that what will happen, you know, if you don't listen to Al, basically. He just goes on and on. He doesn't know when to shut up. So I have the same problem. But there's several problems with this from a physicist's point of view, and that's where I come from. First of all, there are hurricanes all over the place, including this one off of North Carolina's coast. It's got one problem. It's rotating the wrong way. You know. All right. Well, this is a hurricane rotating the right way off of Baja California. You know. You know, the rotations of hurricanes are driven by the rotation of the Earth. So, you know, there's no way it could rotate this way. There's another problem, and here you see there's a massive hurricane here off of Ecuador, you know, and Panama has been flooded, you know, you can, you know, swim from the Pacific to the Atlantic now. You know, Greenland, you know, is all melted. There's a big bay in the north of Greenland. All sorts of horrible things have happened. But it's made up. It doesn't agree with even the most basic science, you know, and this is the level of the discussion that we're trying to face. That it's just nonsense, you know. It makes good press. People get frightened, you know, we're going to fry, all of this crap, but it has nothing to do with science. Talk about hurricanes. We remember that hurricane. This is observed hurricanes. No one has ever seen a hurricane off the coast of Ecuador. Never. Never. And there's a reason for that. I said it's driven by the rotation of the Earth. So if you're on the equator, you can't figure out if you're a would-be hurricane, should I rotate to the right or should I rotate to the left? So you just don't do anything, right? You don't form. Right? So hurricanes in the northern hemisphere rotate to the right, and the ones in the south rotate to the left, right? So that's the level of discourse. If you, by the way, I'm going to give a much more serious physics talk at 4:30 at Chapel. If you really want to go into the physics in detail, you're welcome to attend. But it will have a fair number of differential equations, and maybe you'll get more out of this talk. All right, so this is one of my favorite pictures. You know, here's what the global warming people would like the public to be. Chicken Little running, flapping her wings here, and here is the fox. You can guess who the fox is. There are lots of them. But, you know, if you're being panicked and all you see is panicky stories in the media, you ought to stop and think for a minute, you know, is it to somebody's benefit? You know, cui bono, as they say in the law. And lots of people are benefiting from this panic. Well, let's get back to the basic question. Decarbonize the world is what we're supposed to do. Stop emitting CO2. But you probably remember there's this famous episode where Faust and Gretchen are sitting in the garden. And Faust is wooing Gretchen, you know, I really love you, you know, let's get together. And Gretchen says, well, I just have one question. And in the story, it was, what do you think about religion? You know, but here, the question for carbon dioxide is, if you hold carbon dioxide constant, will that stop climate changing? And the answer is absolutely not. The climate always changes. It has never been stable. You know, as long as we've been able to infer records, the climate changes, and it's not going to stop changing if we stop changing CO2. And the second question you might ask is this the right level of CO2 that we have today? And that's not clear, by the way. I forgot to set it up, but I guess I still have time. I have a little CO2 meter here, which I will put up. And we can measure the CO2 in the room while we're having our meeting here, if I can find a place to plug it in. But you might ask, what is the ideal CO2 level? You know, nobody ever explains that to you. You would think, well, it must have been the pre-industrial level, but pre-industrial levels have been all over the place. And let's see, is there a... Over there, yeah, here's a plug. I'll get it all together in a minute. Okay, so I'm going to plug this thing in. Anybody know what the CO2 level is outside today? You go up a few thousand feet where it's all mixed up. What is the level today? 400 parts per million, right. So we're going to see what it is in our room here. I can plug this in, and I haven't managed to break it. Okay, it's warming up. Well, it'll have to warm up a little bit. Let's see. Well, I'll give it a minute here to settle down. It's got a little laser. The way that works is it's the laser's probing the yeah. Well, the problem is, guys, all of you, your enemies of the planet are sitting in here breathing. And so this poor meter, the reason it's squeaking is that the CO2 levels in here were I'm sorry, it stopped a minute. It's so frustrated they're so high, but it was 1,700. Okay, so the level in this room is 1,700. That's not unusual. In Princeton lecture rooms, it's typically never lower than 1,000. Yeah, 1,800. Okay, so you might think about that. This is this pollutant. We're sitting here breathing this pollutant. You know, it's squeaking because this is designed for heating and air conditioning. So when it squeaks like that, you're supposed to turn up the air conditioning, get a little more air circulation. But that's what it's designed to do. Okay, 1,700. We'll turn it off so the squeaking doesn't drive us crazy. All right, so let's continue. What's the optimum CO2 level? Okay, is it 400? We're doing fine at 1,700. Everybody feel okay? Okay, so in fact, you know, we've studied this issue to death with respect to people because we have people in confined spaces in submarines, in spacecraft. And so we have quite strict limits on CO2 levels in submarines. It's, anyone know what it is? 5,000, yeah. At 5,000, you start, you know, pumping it out. And spacecraft, they're a little more forgiving. You can get up to 7,000 on space flight, yeah. Anyway, but you know, people are going crazy because it's 400. You know, God, the world has never seen 400 before. You know, it's insane. Okay, so let's talk about the optimum level. Well, at 150 parts per million, which was not that much below pre-industrial levels, plants stopped growing. Plants need CO2 to live, and they're not that far from where they are starved to death for CO2. So 280 was the levels, presumably in 1800. We're around 400 parts per million outside today if you go up a few thousand feet. And over most of geological history, the levels have been more like 1,000, 2,000. And this is what plants prefer, actually. Plants are actually starved to some extent for CO2 now. Well, here's a long-range picture of the so-called stable climate of the Earth. You see this is temperature going up and down, and this is the last 800,000 years. This is the last 5 million years. And the immediate thing you see is the climate is never stable. There has never been a history never been a period in the history of the Earth where the climate is stable. We're recently in an ice age, so we just came out of an ice age 20,000 years ago. Here we are today, 0 to the past. So this is the Holocene. But there was a long 100,000-year ice age, and there was a previous warm period like now. It was actually warmer, the previous one. There have been other warm periods in the past, and this has been going on for a long time. People are still debating why this is happening. If you go back 20, 30 billion years ago, this is not the same picture. It's much more stable. CO2 levels were higher too. Just again to point out the instability of climate, this is a picture of John Muir. John Muir was one of the founders of the Sierra Club. He was a smart guy. And in 1879, he made a special trip to Alaska to inspect Glacier Bay. Some of you may have been to Glacier Bay. I'll show a picture of it. But Glacier Bay was first charted, I'll show you a picture and talk through it, was first charted by Vancouver in the late 1700s, 1760 to 1780. So his charts, which were extremely good, showed the bay full of ice right out to here to the strait that goes to the Pacific Ocean. So the Pacific Ocean is out this way. Here's a blow-up of the location in Alaska. Now, ice has been rapidly shrinking, and John Muir came to Glacier Bay in 1879. This is when John Muir came. So yes, indeed, the ice in Glacier Bay has melted, but it all melted, almost all of it melted by 1879 when John Muir went there. So it's true that glaciers are melting. Nobody's kidding you there, but it has nothing to do with the Industrial Revolution. It started a long time before there was an Industrial Revolution. And exactly what has caused this is not clear. Some of it may have been a little temperature change. Much more likely, I think, is changes in snowfall at the headwaters, or whatever the right word is, of the glaciers. If you get less snow, you get shorter glaciers. There's nothing to feed them. But anyway, it's not connected with the Industrial Revolution. Well, okay, so what's the fuss about? The fuss about is CO2 is inexorably going up. So here's CO2 levels. I mentioned it's about 400 parts per million now, so we're about there to 2014. And supposedly this was to cause enormous warming, but the blue here is temperature, and in fact, there was a cooling period up until almost 1980, then there was warming till about the year 2000, and then it's been flat or slightly cooling again since then. So the actual observed temperatures don't look anything at all like CO2 levels. By the way, this oscillation up and down is winter and summer. When it's summer in the northern hemisphere where most of the land is, all the plants start to grow, the forests, they suck out CO2, lower the CO2 over the whole world. And so you have a summertime of low CO2, and winter comes, it's dark up there, nothing grows, the CO2 recovers a little bit. So there are these oscillations, and on top of that there's this upward drift, some of which may be due to fossil fuel burning. If you put all the fossil fuel that's burnt as CO2 into the atmosphere, however, this would be increasing at twice the rate. So about half of it is not making it to the atmosphere. Most people think it's going into the oceans, but even that is not completely clear. Here's another picture of the summer-winter cycle. So this is year going this way. This is the northern hemisphere. This is the southern hemisphere. So you see these huge cycles of CO2 levels up and down, winter, summer in the north. Much smaller in the south because there's precious little land in the southern hemisphere. If you look at the globe, most of the land is in the north. There's a little bit of land, South America, Australia, but it's mostly ocean in the southern hemisphere, which does not have this property. Okay, I mentioned historical levels. This is the Cambrian era when we started getting really good fossils, hard shell fossils, 550 million years ago. Ordovician, Silurian, the geological eras. And this is CO2. The main point to notice here is the scale. The scale is in thousands of parts per million. It's not in hundreds of parts per million. So for most of the Earth's history, CO2 levels have not been measured in 400 parts per million or 300. They've been measured in 1,000, 2,000, 3,000, you know. And the Earth was fine. It was full of life, dinosaurs, goodness knows what. There were even some of our ancestors back then. Didn't seem to mind. All right, so, well, what is the physics? Well, this is actually a pretty good picture from a NASA website. The Earth would be unlivable without sunlight. It would be much too cold, and a little bit like Pluto, you know, out at the fringes of the solar system, which is frigid cold because it doesn't get enough sunlight. So we're lucky to have the sun, and the sun warms the surface of the Earth, and you have to get rid of some of that heat or it would warm without limit. So some of the heat is radiated back into Earth as infrared radiation. And if you look at the Earth with infrared instruments from space, it's glowing like a hot coal in a fireplace, and that's the cooling radiation from the infrared. In fact, NASA's about to launch some really interesting experiments to look for, you know, glowing Earths out beyond Pluto. They may be there. No one has looked. So, you know, no one is sure whether there might be lots of Earths, you know, way out at great distances from the sun. Anyway, supposedly what CO2 is going to do is greatly modify this cooling cycle, so it'll be harder for the Earth to cool. And therefore, in order to make up for that, the surface is supposed to warm. And so that's the essence of the argument. Yeah. You have to understand a little bit about the way the Earth's atmosphere works. The Earth's atmosphere has about 10 kilometers of troposphere. This is the region of the Earth where there's churning of air up and down, clouds are forming, rain is falling. And so most of the heat is transferred from the surface upward, not by radiation, but by the motion of air, especially air that's humid and that's carrying the latent heat of water. So you can think of this first 10,000 meters, first 10 kilometers, as a little bit like a boiling pot of water. Unlike water, it's air, so it gets thinner as you go up. There's not so much weight on it, so it decompresses, and as it decompresses, it cools down. So this is very basic thermodynamics. And so for the engineers and physicists, this is a part of the atmosphere where the entropy per mole is almost the same at the surface as is at the tropopause. And then at the tropopause, the Earth's atmosphere stops churning. That's where airplanes like to fly. So they try to get out of this churning so you get a smooth flight. And up here where it's the stratosphere. So there's still a little bit of convection, but very little in the stratosphere. Lots of left-right convection, but very little up and down. And then there's heating as you go higher in the stratosphere. So the atmosphere warms up again. This is ultraviolet light heating ozone. And then it just continues up, getting thinner and thinner as you go up. So this is the Earth's atmosphere, the Earth that we live in. And this is a little more detail about that churning that I mentioned, the boiling of the troposphere. It's actually somewhat organized, and you have lots of air rising up over the tropics where the sun is shining hottest. And it comes up carrying lots of water vapor, so you have very massive thunderstorms along the equator in the tropics, and some of it heads north and some of it heads south. By the time it gets up to the top here, it's been stripped of most of the water, so it's very cold and very dry at these high levels. And it's cooled and dry partly because it's radiated energy out to space here, both from cloud tops and from CO2 and from water vapor and various other things. Then it comes down at about 30 degrees north or 30 degrees south as a very, very dry, dehumidified air. This is the belt of deserts. So this 30 degrees is where the Sahara Desert is. It's the Sonoran Desert. You know, the Atacama Desert down here in South America is the mirror image. And then there are other convection cells all around. So this is a complicated planet that we live in. And it's no wonder that you can get any answer you would like. If someone asks you, how much you want me to warm the earth for you, sir? And, you know, well, how about 4 degrees? Okay, you got it. And so that's basically what's happened. I can assure you that they haven't got a clue of how to do it from first principles. Yeah. All right, well, let's talk a little bit more about CO2. CO2 is a linear molecule. It's got a carbon atom in the center and 2 oxygens. At rest, it's just a straight stick like this. But it can vibrate. And there are 3 atoms. There are 3 modes of vibration. And there's one in which the carbon moves to the right, the 2 oxygens move to the left. That's called the asymmetric stretch. That absorbs and emits radiation very strongly, but it's outside of the thermal emission spectrum of the Earth, so it has almost nothing to do with global warming. The real villain, I like to call this Satan's number, but this is the bending mode of CO2 at 666 waves per centimeter. That's the units that people like to use for this region of the spectrum. And that's what contributes to greenhouse warming, along with many other things. Notably, water vapor and clouds are by far more important. And finally, it's got a symmetric stretch here where the carbon sits still and the 2 oxygens move left and right. This actually doesn't absorb radiation at all, so it's almost irrelevant except that it perturbs these others. So if you want to learn more about this, come to the physics colloquium. I'm not going to say any more about it here, except to say that if you now look at what this does to radiation, what I'm showing here is what is the probability, what is the fraction of radiation that comes in at the top of the atmosphere that reaches the surface, or that's absorbed, I guess, absorbed here. So going up, it's absorbed. So there's an atmospheric window where we look out on a clear day and we see the beautiful blue sky and the sun. And this visible spectrum here, this is wavelength here, so these are wavelengths that you can see, half a micron, 5,000 angstroms. There's another narrower window out here in the infrared where the Earth tries to radiate. So the Earth is a warm body like a coal in a fireplace, and it's trying to send its radiation out to space, and some of that gets through this window. And so the allegation is that because CO2 is at the edge of this window, it will narrow this window, and so the Earth can't cool as well, and so it'll have to get hotter at the surface. But you can see already from this, the big gorilla in all of this is not CO2. This is the CO2 absorption band. It's mostly water. So water, this is the rotational spectrum of water, the fact the molecule is tumbling round and round. This is the bending mode, much like CO2 of water. There are higher modes out here. But the basic physics has to do with the radiation transport and these molecules. So let's talk about the facts. So it is true that there's greenhouse warming to the Earth. You know, if there were no greenhouse warming, the Earth would be too cold to live in. Even with the sun, it would get warm enough briefly during the day, and then it would cool off immediately at night, like being in the desert. So it would not be a nice place to live. And so we're glad to have water, CO2, and the greenhouse effect. And more CO2 certainly will cause some warming. So the issue is how much warming. It's not that it's impossible. Of course it's true. But a tenth of a degree of warming is different from 10 degrees of warming. And the real answer is probably about a half a degree, between a half a degree and 1 degree of warming centigrade degrees if you double CO2. Okay. So most of the models predicted in the last 20 years we'd have had 3/10 of a degree of warming, 15 years, going from 370 to 400 parts per million. And the observed temperature change has been essentially zero. It may actually be slightly negative. So there's something seriously wrong with the climate models. They really don't work at all. People often ask me, who are you to jump into this? You don't have a union card to be a climate scientist. And so I like to point out that I was the co-author of one of the very first books on climate science, before many of the alarmist climate scientists were even, in grade school. So in 1982, I was co-author of this book. I had the part related to radiation transfer. And so I've been interested in this for a long time on a very professional level. And so here's how well I did. This is me and my colleagues. This is the warming we predicted. And this red bar is what's observed. So we were right in the middle of the pack. We got it as wrong as everybody else. Yeah. So I mean, that gives me a certain amount of humility. But in fact, the observations show the Earth simply is not warming. There's something seriously wrong with these models. And we can talk about this later. You know, there are all sorts of, the last I looked, there were 30 different proposals of why this is happening. None of them with the courage to say that, you know, the basic reasons they've overestimated the sensitivity to CO2. Okay, so, but the press is noticing now, this is from quite a left-wing German, Der Spiegel. And it says here, this last year, it says climate change, researchers are scratching their heads about the pause in global warming. You know, so the black bars are the observed temperature of the Earth, and the various color bars are the fancy computer models, all showing rapid warming, observation showing no warming. This is a couple years later now, it's still just the same. In fact, it's pulling out from below the lower edge of this now. So it's not working. So these are satellite measurements of the temperature. One problem in all of this is getting reliable data, because a lot of the data is fiddled with to try and make it fit what the politicians would like. And so it's amazing if you look at the data for the temperature of the U.S. today and you look at a similar copy 20 years ago, they're not the same at all. You know, for example, the Dust Bowl has gotten a degree or two cooler than it used to be. Reminds me of, you know, the old Soviet Union. They used to joke the hardest thing to predict is the past, because they were constantly right. Okay. But anyway, satellites show no change also. And by the way, this is not the surface. With a satellite, what you do is you look down at basically radar emissions coming up from the oxygen in the atmosphere. So you're doing radiometry on 60 gigahertz. If there are any engineers here, they know what I'm talking about. And so that only allows you to get down to maybe a few thousand kilometers. And at that altitude, it should be warming faster. So warming should be greater in the lower troposphere than the surface. But actually, there's no warming there either. And this is where you really ought to look. It's not there. You can see several things. Here's a big El Nino spike. That was 1998. One of the biggest El Ninos in the last few decades. There's a lesser one we had not so many years ago. There may be another one brewing later this year. It's not clear. It would help to give some rain to California if it would show up. But an El Nino, you read a lot about it. Let me just briefly explain what it is. Normally, here's the Pacific Ocean. There's North America. There's Florida. Here we are in Raleigh up here. Just barely made it on the map. There's Australia, Indonesia. There are persistent trade winds normally along the equator blowing from South America toward Australia, you know, from east to west. It's because of this Coriolis force I mentioned to you earlier that Gore doesn't understand. And, but every now and then the trade wind stops, and then all this warm water that's been shoved up against Australia drifts back, sloshes back to South America, to Mexico, and we have a huge patch of warm water that used to not be there, and so the whole Earth looks warmer during El Nino just because there's more exposed warm water on the surface of the ocean than there normally is. Occasionally you get extremely strong trades, La Niñas, when you really drive all the warm water down here, and then the Earth looks a lot cooler. Of course, the heat is the same. It's just how much is exposed that you can see from outer space. Okay, well, let's talk about agriculture. So when I give this talk in many parts of America, people don't know much about agriculture, but I hope people do here. So what crop is this? What's this crop? Soybean. Soybean, very good. And has it been genetically engineered? Yes. That's good. Good. All right, so they're good people. All right, so you have to know what soybeans look like, but the fact that there are no weeds means it's been genetically engineered. Yeah. Okay, so that's Roundup ready. Okay, well, here's what happens when you test growing plants with more CO2. This is Sherwood Idso at the University of Arizona. This is ambient CO2 levels of pine tree. I've forgotten which variety. It's not loblolly. And this is, you increase by 150, 300, 450, and you can see trees love it. You know, all plants love it. There's the actual experimental setup that you surround it with these polyethylene things that let the sunlight in, and you measure the growth rate. These are various crop plants, ambient CO2 100%, and here's a cam plant is something like a cactus or a pineapple. That's the only thing I can think of we actually eat that's a cam. It's an unusual photosynthetic path, but most of our plants are called C3, and so that would be things like wheat, soybeans. There are a few very important plants that are C4 plants, and one of those is corn. That's a C4 plant, and sugar cane is also. So no matter what the photosynthetic pathway is, all of them do much better if you increase CO2 by, this is roughly doubling here, not quite doubling. And this is far from saturated. If you double again, you get even more yield. And here's the reason for that. If you look at a plant leaf, the plant gets its CO2 from the air. It doesn't get it from the roots, not like nitrogen or potassium or phosphorus. It has to get it from the air. And so in the leaf, there are little holes, stomata, I think that's Greek for a little mouth. And so into these stomata, CO2 molecules diffuse, and the molecular machinery of the plant grabs the CO2 molecule, fixes it, turns it into sugar or cellulose or something that it needs carbon for. But for every CO2 that diffuses in, there are roughly 100 water molecules that diffuse out. So the plant has, as a chemical plant, something growing has this trade-off it has to make that it doesn't want to dry out by losing all of its water through the stomata, but it still needs to get enough CO2 to grow. And so plants are extremely sensitive to the levels of CO2. So if you double CO2 levels, you find that the number of stomata goes down by a factor of 2, so there are fewer stomata. And so that's one of the ways that we can estimate past CO2 levels on the Earth, that you go to a peat bog or something, and this is an actual picture from a peat bog. This is a dwarf birch leaf, and this is actually a photograph of the leaf. And this was a measurement, you can read it up here, in Denmark. And by counting stomata, this guy inferred that at that time CO2 levels were about what they are today, 400 parts per million. It's a very controversial paper. People can't figure out, if that's not the explanation, what is it? But anyway, so stomata are very important. And it's why plants do so much better with more CO2. Stomata is a bad thing to have, other things being equal. You don't want them because they dry you out. And so, you know, if you're a greenhouse operator, you can go to the internet and you can buy a CO2 generator. And it turns out the cheapest source of CO2 is not a bottle of CO2, it's a tank of propane. So if you're running a greenhouse, you buy propane, you put it into this thing, you burn the propane, you throw away the heat, and you put the exhaust into the, into the greenhouse to make your plants grow better and get a better price for your product. It reminds me of William Faulkner's recipe for hush puppies. You know, you go catch a bunch of catfish, you get a big pot of oil, you boil the catfish, and then you make the batter, and you batter the catfish and dump the hush puppies in, then you throw away the catfish and you eat the hot puppies. So that's sort of how this works. Right? All right, so if you look down from satellites, you can measure the chlorophyll on the Earth, and what this is the last 20 years, I think. You can look this up. Here's the reference. But you notice there's greening all over the Earth. So this is a measure of the greening, but especially in arid regions. So the west of India, the Sahel, southern edge of the Sahara, Western Australia. And almost certainly this is the fact that these plants here, they have measurably fewer stomata, so they don't need so much water as they used to need. And you can test that in labs. There's central Turkey, it's dry there too. So CO2, far from being a pollutant, is actually making the world a better place. Well, people keep talking about starvation. This was when Paul Ehrlich published the population bomb. He said the Earth would be a shambles by now. We'd all be extinct. Nothing he predicted in the book was correct, except that his author's now chief science advisor for the president, his co-author John Holdren. Yeah, so that's your reward for predicting everything wrong. But anyway, this is wheat yield in India versus time, and it's increased by more than a factor of 10. It's still going up. And so in fact, India has a problem with wheat. They have a surplus. There's not a big enough market to eat all the wheat in India today. And so they're a major player in the world export market for wheat now. And they were all supposed to be starving to death today. Yeah, what nonsense. Well, I won't get in trouble. You keep hearing about extreme weather. Well, here's the facts. This is supposedly more CO2 is causing the weather to be more extreme. Well, the weather is never terribly stable, but this is tornadoes per year. This is today. This is going back decade by decade. This is northern hemisphere snow cover, no change, really no trend. This is hurricanes, no trend. Drought years, wet years. The climate changes. When I was a kid in North Carolina, there used to be a proverb, what's impossible for God? And the answer was to please a farmer. Whatever the year is, it's too hot, it's too cold, it's too dry, it's too wet. You never can get the climate right. Yeah. Okay, pH, you hear about ocean acidification. This is an actual experiment where they took a ship and sailed from Hawaii to Alaska and measured the pH of the ocean the whole way. This is the pH. You see the pH of the ocean for the chemists in the crowd. It varies from way above 8, near the equator, down to about 7.3 or so. It's still alkaline over the entire range. It's very depth dependent, so up and down is the top of the ocean. This is the bottom of the ocean. This is Hawaii. This is Alaska here. And even on a single day in a patch of ocean where the sun is shining on it, the pH level goes up and down by roughly 1 unit, just because of photosynthesis. During the day you suck all the CO2 out to make sugar as the algae, and so there's not enough CO2, so it gets very alkaline, and then at night it gets acid again, so it fluctuates up and down. So it's nonsense. Sea level rose enormously when the ice sheets did 12,000, 10,000 years ago, but it's quite stable now. It's increasing at a rate of 2 or 3 millimeters per year. There's no change whatever in that rate. There's no sign of any effect of CO2 on that rate. Here's a slightly blown up version of the sea level rise. And it fluctuates. It was actually falling up until about 1850. This was the end of the Little Ice Age, when it was really very cold everywhere, and sea levels were dropping then. This is U.S. emissions of CO2. You can see that we peaked in the early 2000s because of the switch to natural gas. So we're burning less coal, more natural gas. So we're the only major country in the world in which CO2 level emissions, they're going down. And that's because of the fracking revolution. This is comparison to the other countries. This is China. This only goes to 2010. China is now more than double the U.S. So it doesn't matter what any other country does as long as China and India is close behind. Don't slow down. I don't see any reason for China or India to slow down. They need to become prosperous, and I'm all for that. They should put on precipitators, to get out the fly ash. They shouldn't burn high sulfur coal. They're an obvious thing they shouldn't do. but CO2 is not one of the issues. Okay, so here's a summary. Policies to slow CO2 emissions are based on their flawed computer models which exaggerate warming by factors of 2 or 3. More CO2 is an overall benefit, so the mitigation schemes actually do harm. They not only don't do any good, they actually harm what we could have. And so closing thought, this is my friend Schopenhauer. All truth passes through 3 stages. First, it's ridiculed. Second, it's violently opposed. And third, it's accepted as self-evident. And I think right now we're somewhere between 1 and 2 here, between ridicule and violent opposition. For example, if you read Matt Ridley's op-ed last week in the Wall Street Journal on CO2, more or less the talk I just gave. He sent me an email yesterday saying that he had just been mercifully hammered by all of the right-thinking people from from the CO2 cult, and so violent opposition is certainly true right now. Yeah. So let me end this by playing a little tape for you to close. And being a physicist, this is a physics-related tape. Involves one of my heroes.
Questions for Dr. Happer, if you like?
Doctor, global warming potential. CO2 is a 1, and there's some other chemicals out there. Let's say there's one out there with a global warming potential of 100.
Right.
Does that literally mean that the chemical with the 100, every 1 part per million that goes up, it's equal to 100 parts CO2 going up? You know what I'm saying? Is that?
Yes, but what they don't tell you is that CO2 is now heavily saturated in that it's done most of the warming it can possibly do. So if you look at this is warming this way, this is CO2 going this way. The curve goes up and it's flattened out. And so that, if you were to look at the CO2 molecule at the beginning at the same concentration as this super molecule you mentioned, they would have almost the same potentials. So it has to do with the fact that CO2 is in its saturation region.
Because I wanted to make a debate with people, like water vapor, and I want to say to them, why are we not worried about these other chemicals with global warming potential of 50?
Well, water vapor clouds are the major thing. Right. It's hard to get even close to either of those. Yeah.
Where's methane?
What's that?
Where is methane in all of this?
Methane is a little bit like the gentleman's molecule here. It's far from saturated. So you measure methane in parts per billion, whereas CO2 you measure in parts per million. So there's 1,000 times less methane. And since it's in an unsaturated region, there's not very much of it, so a little goes a long way. So indeed, a little methane causes more warming, but methane is right in the middle of the water, the edge of the water absorption band, so it has a hard time competing with water vapor. Another big difference with methane is that methane doesn't live very long in the atmosphere before it's oxidized. It collides with an OH radical and it gets converted to CO2. And so it's unlike CO2, which lives for a long time. It gets absorbed into the ocean, but it can come back. Yeah.
Is that the same for ozone?
Well, ozone, again, it's very unstable at where we live on the surface. And yes, it's similar to that. It's an unsaturated molecule. It's unsaturated absorption. But ozone has much more serious issues than global warming. If you get too much ozone, you ruin your lungs. And so, as opposed to methane, which causes you no harm, or CO2 causes you no harm, ozone really does chews up your insides. Yeah.
How do you think the public debate is going to play itself out on this? I mean, we're in the violent opposition phase.
You might want to repeat the questions.
Yeah, how do you think the public debate is going to play out? Well, I don't know. I mean, it's kind of interesting. Some politicians have bet their careers on, sort of the green support. And Al Gore was one of the first, but he wasn't the only one. In Australia, they made that bet. And the government was resoundingly voted out of office just last year, 6 or 8 months ago. So at least the experiment has been tried in Australia, so it was a disaster for the Greenies. They lost control of the government.
We have time for one more question.
Yeah.
To get to UNC.
Yeah. Yes,
worry about a sort of blacklist effect? People with your views?
Well, there's lots of people who take violent exception. You know, I occasionally get a postcard with a death threat. You know, I put it in the garbage. And phone calls, you know, to me and my family. The people that I respect, you know, fellow physicists for the most part, engineers, are quite open. You know, many of them agree with me. So I think, I may have said before, that this idea that the scientific community is fully aboard, nothing could be further from the truth. They're all, I think, they're quite worried about the long-term effects on scientific credibility. Yeah.
Doctor, thank you so much.
Oh, okay.